to thank Laman Kalantari for the opportunity to hold this talk. And of course, mathematicians are very precise, and I thank him for the opportunity to pronounce these words of recognition. And of course, we're very precise, so I have to add a footnote because I have to thank him for the opportunity to pronounce these words of this footnote. But we have, of course, to be very precise, so I have to thank him to pronounce these words of thanking. So it means that I could go on like that, but of course, mathematicians have a solution to this, because you can introduce the nth word of thanking, and then you simply put 3 dots, so the algorithm of thanking, the loop, can be interrupted. So, Laman, I thank you. The topic is unusual visualizations unusual methods of mathematical visualization. I do a theater show in Belgium with African music, and actually my goal is, it's something I already exercised 3 or 4 times, what I will do now, but always in different situations before I do the theater show. I just do some tryouts now, and this is actually another tryout. So the goal is to have things that I can show on the scene. You cannot show images on the scene because the people have see too many images. They see images on TV and so on computer. When they go to a theater, you must show something that is lively, that comes alive. So that is the goal. It will be with a house music group, by the way, not with this music group. This was for the African situation. One example of such an unusual visualization is this. Here you will see me engrave the first decimals of the number pi in 0 gravity. I'm very proud of this. The first decimals of the number pi in 0 gravity. Here they are. Weightless decimals. So this is what I intend. Another thing that maybe you know very well is our stereograms. I will skip this part because I think you know that. But I find this very surprising. It gives a very good effect if you have time to do it on a scene. People stare at it and they see the Ashango bone in it, for instance. I have copies with me, but we won't have the time to do that. I think actually that, for instance, for knot theory, this is really useful because I have spent evenings staring at knots, at this knot, for instance, because then you can see 3D images in there. They pop out. I think you know that, you're familiar with stereograms. On the internet you will find 3, I think at maximum 4 stereograms about knots, but not complicated knots. And the advantage is that you can see where they cross or overlap or not, because you can really see it on your computer screen in 3D. Okay. How to make it, you find it on the internet. So that were 2 examples of unusual things. When I talk about unusual things, I have some conditions though. The unusual method, to me, it must add something to the mathematics. A 3D stereogram is important for knots because it adds 3D, a 3D view. It's not just to make a 3D image of something, a 3D image of the number pi or something. No, because it adds something, it's useful. The 0 gravity, for instance, that was not just a joke, it was actually a metaphor for the opening scene of 2001: A Space Odyssey. And with that, we could convince CNN to make a little item about the topic. So it must be useful, that unusual method. So we have to avoid a gadget type approach, because of course when you teach mathematics or when you have a theater show in mathematics, you don't want to waste your time with too many gadgets. You want to, well, convey something. This, for instance, you can find it on the internet as an illustration for the cardioid, but I think this is pretty useless because it doesn't add much. So this I want to avoid, so not anything goes, but I think even mathematical art can be avant-garde. What do I mean by that? You know, this example, this pot here was sold, this is art by a Dutch artist. It's sure that it's art because it was sold at Christie's for $355,000. So that can be the case for mathematical art too. It shouldn't always be nice, fancy illustrations or models. I think it could be a bit non-aesthetic. 3 main examples: with black light or with light. Another one with lasers, because with black light it adds some mystery, and lasers, they know that from Star Wars, and that's what we will do immediately. And we will do something about the art of gastronomy. In Belgium, we will consider this an art in Belgium. That was a joke. Here we have an example of such a blacklight thing. I handed this out to some people yesterday. Here you see the beginning of counting. You see some Arab numbers, you see some Hindu numbers, music notes, and so on. So during the day you look at this card while you study your mathematics, and then at night you switch off the light, and what do you see? You can test it with the cards that I gave you. At night you will see this, you will see Africa at night, and you will see that the brightest star is Shango. Here you have South Africa, and there you have the source, you have the Nile, sorry, there above. So this is something that the effect of black light adds to it. Another example of this use of black light are with these models. When you show models on a theater scene, it's good that they see only the model, so not the person behind it. Here I've cheated it a little bit so that you can see that somebody holds it. You know these models from Rinus Ruloff's talk, but I want to do it on the scene, that is with a real model in paper so that someone can open it. And I did this here, I put a little puppet in there so that something magic pops out of it. And this is then like in a magic trick, and you know that you can transform it in a cube, and then that little puppet doesn't go in there anymore. Another example is of use of blacklight is this here, something done by my students. You know this from the book by Doris Schatzschneider and from other. It has been already in one of the talks here. What did they do? They said, well, I can design this fancy lamp as follows. I had some blacklight, and if I turn this kaleidoscopical lamp, I get another lamp, and I get another effect. Okay. These are two examples. This is something that I personally like. You know this from the work. Several people show this normally in this kind of conferences. But the problem is to guess, when you show this to people, to guess what is the polyheder inside there. So people always explain that there is a polyheder inside, but you cannot really see it. Some of my architecture students said, well, we will solve it this way. We will put some light, but then you still don't see it, because you see a lot of light here. Other students had another solution, and they solved the question as follows. There are the students here, and they solved it as follows. They put black light in here, and now you can see just the intersection and not the rest. So you can clearly see the volume as such, and not the construction to make it. Once more. Okay. So we will try to do this, and I choose here on the scene, and I'll choose this example because you can see here this Yoshimoto cube in the Museum of Modern Art. I just learned 2 days ago in a conference that Rinus Ruloff held in the Ruby Tuesday restaurant at the Holiday Inn here, that it was actually made by, first discovered 1 year before the Japanese person, by Anton Hanegraaff, isn't it true, Rinus? So, well, we will try to do something with this little object. Here we go. I need, please go on. I need my gloves. I made this model that you can find on this website, because I've seen it in a conference in Germany, of course, this model. And you can also find on the internet how to do it. You have to wear gloves for these kinds of things, because the goal is, of course, the gloves, it's much easier with the hands, but it adds something to it that they don't see your hand. See? Make it a bit darker. It's hard to push from the computer with gloves. Okay. Oh, yes. First, we need black light. I need an assistant to hold the black light. Just hold the light.
Volunteers from everywhere.
Yes, Mama. I see that you're a volunteer, okay? Good, so the organizers will do a lot of things here. And just shine in my direction, if it works. Yes, it works. Shine in my direction. Okay, good. So, the story is that you see this cube, a cube.
Oh,
then you can tell a story that the Greek were thinking about how to double the cube. So, you fold it, and there's a star coming out. And the Greek will say, of course, we will have to look at the stars.
Can you take off your badge?
Stars, and they will say, what can we see in the stars? We saw one cube already. Here, one cube. And here, another cube. I need a table for that, of course. Here I have it. Where do I get another cube? Here, another cube.
Can you take off your badge, sir?
Yes.
Thank you.
Thank you. Well, it was actually to show my name.
We know your name.
Right. So we have doubled the cube because we have a look in the stars.
Where? Oh, there it is.
No, it's part of the goal to show.
Woohoo!
Okay, thank you. I want to do this with many more volumes, but I brought this one because it's the smallest one. Something else I want to do, thank you, is you know this theorem, Pascal's theorem. I don't need to explain it, but it's good to see it so that you know what you'll be doing. The thing is, you do this with lines, and of course with lines, with a rule, or with a computer, you're never sure. When are you sure? Today, for your students, when you can do it with a laser, then you're sure. So you will try to do this with a laser. It's more fancy, and some of my students actually did this. They made this, you can see it here, they made this illustration, and they made this little movie about this theorem. This was the movie. And now I will try to do the same thing. I saw this from my students, so I said, if my students know how to do this, maybe I can do this too. And I try to do this for just generalization that you know with the conics. And I said to myself, maybe I can do this without an expensive laser, with just using some laser pointers. And this is what I will try to do. I need someone to help me. Eva, yes, there you are. You will point at the intersection of the points here at a certain time when you see them. So what will you see? This here, this situation. Eva, as soon as you see appear these 3 points, you point through them to link them and to prove the theory. Here you go. Okay, switch off out all the lights, please, all the lights. Eva, come closer. Oh, no, wait. I know. Next to this, right? This is what we'll do. Oh, sorry, forgot something. Something else is with cooking. Some of my students made this cooking program. As you can see, it starts like any cooking show with broccoli, because I know that someone in this room likes broccoli a lot. In the Ruby Tuesday restaurant, half of the meals go with broccoli. And so they're still showing it there. We won't look at the movie. what did they do? Here they play the following role. Normally in those shows, I don't know how it is in the States, but the man is the wise cook who knows everything, and then the woman just helps him and cuts a few carrots or something. But there it was the opposite. At a certain time, she starts explaining the properties of fractals to the cook, actually. So it's a bit very gender friendly. So that was something that happened. This is something I would like to do on the scene. Cooking on the scene while the music plays. Together with this, of course, we are very well known in Belgium for French fries. Actually, it should be Belgian fries. This is a new invention by Belgium. It's the hexagonal French fry. Because the square one, normally French fries are square as an intersection. So he says if you use a hexagonal intersection, you have less grease and less fat. And it's actually proven experimentally, you get 10% less calories. Now you could say, maybe we could use octagons, but if you use octagons, you lose a lot of potato. So it's better to do, the best solution is, you could do it with circles, but then you lose even more. So that's why cooking some, and here you have the grid to cut these hexagonal French fries. So this would also be interesting to do on scene. Okay, well, she is helping me there for the last demonstration. Something else that students did is the following. The hyperbolic paraboloid, because as I said in the previous example with French fries, I don't need to explain that the mathematics behind it is that you get less circumference. The other is explaining things about the kitchen program. Well, yes, okay. So they were explaining a few things, and then there's some mathematical intervention there. So I let them cook. The thing is with the French fries that it explains that you have less circumference for a given volume with the hexagon. Here, for instance, what is the advantage here? If you have a hyperbolic paraboloid and you put it on a table, then you can make it much thinner as a surface. Because of course, when such a surface, you combine this form, this shape. If you would turn this shape over, it would break immediately if you push like that. But like this, it's very stable. So what you can do, if you use this shape, you have a shape like this, plus another one like that. So if you turn it now, it's always very stable. So that's the goal. And actually, this is not new. Pringles are in the shape of a hyperbolic paraboloid. So, but since we are from Belgium, of course, we wanted to make hyperbolic paraboloid chocolate. And some students try this, and it's not so easy, because you must find the procedures to do it. You cannot make a circle just on using any form, because you would poison the clients. So, in the first year it was not successful, they couldn't do it. But then there were other students who could do it, and now they are selling hyperbolic paraboloids with nuts, milk chocolate, and so on. And, here you can see it in the shop, and here it's already on the radio. To be honest, now it has stopped. There's a little problem. Okay, but we once did it. Something else that I normally do in such a theater show is with cheese. I cut it into parts, and I think I don't need to explain what the goal is to show that the number pi would be if the number pi would be a fraction. And if this would be a rational number, and this a rational number, then this cheese would be equal to that cheese, so pi would be a fraction. So what do I do then? I take a piece of cheese and I cut it, let it cut by a volunteer on the scene, showing that pi is irrational. For pi squared, I use donuts, of course, and if you can cut a donut in such a way that you get a prism with base, height, and depth that are rational numbers, it means that pi squared would be a fraction. Normally I do this with sausages on the scene, but I adapt it here to the local situation. In Belgium it's of course like in Germany with wurst. So you will see that this is important for the next example. Capraf meant the golden section once more, if this is the golden section. But the inverse of the golden section is 1 over 1/6/8, etc. This is this number. This is 61.8%. If you divide a line in 61.8%, and then you have another 38.2. I take this part, I put it there, and this, I imagine that these are holes, that these are openings. I redistribute them, and this little part, I put it there, and I also redistribute them. Then I use this for a salt pot like here, and it's here these holes are the same as over there. So white hole, no hole, hole, no hole. Here you have it, open, close, etc. So it means that here you have 38.2% openings. Here you have 38.8% openings. No, it's different. Here you have 61.8% openings. Here you have 61.8% openings. So if you slide them over each other, you get less openings. You get 38.2% openings. So you have this with salt pot, so you can slide the two over each other. And that means that you can put, for instance, 61.8% of salt on the cheese and 38.2% of salt on the wurst. You can eat them together, and if you eat them together, then you will have a 50% salt taste. So a golden section salt taste. Okay. Yeah, 5 minutes. I know. I'm done. This is my last example. My last example is this ice cream. You know this theorem of Dandelin. I have a watch in front of me here, Helena. So you know this theorem of Dandelin. It has already been mentioned. It's also called the Belgian theorem. And what is, as I'm doing there, she's illustrating it with ice. You can also illustrate it in 3D. We once did this. This is the goal, to do it with a cone normally. We did it in Ostende. We sold it in the local casino. And here you have people who are eating this mathematical theorem. And there were explanations about the mathematics on a sheet of paper under the ice cream. Here we will do it. Oh, we were very successful with this because even Miss Belgium came to the opening ceremony to eat the ice cream. She wanted to show Miss Belgium. She did it for free because she thought that doing something with mathematics was good for her image as a Miss Belgium. Okay. Even our Queen Paola saw it, and Jean-Marie de Donker was so kind to show the Belgian theorem to our Queen, and she was very happy. This is what we are doing here with this ice cream. You can check this. It's this model. So you can also do this with a cylinder. Here it is. So what is the goal? You put the sphere in there, another cookie. This is the cookie. The cookie is an ellipse. If you put the cookie in there, that is an ellipse, and another sphere, the two spheres will touch the ellipse exactly at the two foci. This is the theorem. So what you do, you take out the cookie, and you can check where there are some ice cream spots. It should be at the foci of the ellipse. So you learn some mathematics while doing it. Please check, Eva. Okay, one more minute. This is what we are doing. And of course, I have high hopes. This is the poster about the decimals of the number pi. Here it is shown that the decimals of the number pi are random. You see this in colors, because there are no colors that are repeated. It's not like some wallpaper. But I also did this in chocolate. And in chocolate, it's the following. These are pralines, Belgian pralines, but actually they are not pralines, they are tiralines, we say. And every digit is, not enough time. Every digit has a special taste. 0 is strawberry, 1 is simple berries, blueberries, 2 is plain chocolate, and so on. So every digit has a special taste. So what you do when you want to follow the number pi, you eat the digits, you start with 3, and you have berry. Then you eat the number 1, and you have the taste, 1 was berry. So, and since it always changes, the more you eat, it always changes. At first it's 100% berry, then you add something of this, of that, so it always has an unexpected taste. We have specialists here of random numbers. There he is. Doug, can you distribute it to everyone? And then I will conclude. You distribute to everyone, please. Everyone, you take a random number, please. Take a random number. So, of course, I have high hopes. I will not only do this visually, but I'm also dreaming, and actually I'm already very far of doing this with music. Contrary to what someone said today, you can make music with random numbers. I think it's self-explaining. Every note corresponds to a digit, and you get some house music. I know that house music is very popular. You know that in Europe, but also in the Midwest of the US. I just heard this. So what is my goal? My goal is that one day I will be on the scene with some house musicians, So it will be house music featuring Dr. Huylebrouck, the Dr. Huylebrouck project, and maybe he will be there with his keyboard, and I will be at his side with a big calculator. Thank you. That's it. It's time.
That ending couldn't have been made any better than that.
Please eat all the chocolates, please. Because I will not bring them back to you, because the chocolates from Bruges, the city of chocolate.